So I already been presented, and so full professor of mathematics, have the Laboratory of Cryptography at the Università of Trento. I have this national role in the Italian Association dei Componenti Cifris, which gathers Italian cryptographers. I'm also president of the scientific committee of the foundation, Quadrans Foundation. But then I'm also now a part-time professor because I'm very busy with consultancy work in cryptography and cybersecurity, algorithms and protocol. I design them, I prove their security, I evaluate them. And recently I've been asked a lot to do this ransomware, malware analysis and decryption of files. Okay. So, what is a blockchain? This is blockchain, in my opinion. This mess that you see here is a blackboard which is infinite, immutable. Everybody can write anything and that remains. Okay, get back to that. Now, cryptography mathematics. 1939, Adrian Albert, at the conference of the American Mathematical Society keynote speech, a famous speech, where he says that cryptography is more than a subject permitting mathematical formulation. It would not be an exaggeration to say that abstract cryptography is identical with abstract mathematics. So at the time, people started to understand the strong link between mathematics and cryptography. 10 years later, we have Shannon with his landmark paper, Communication Theory of Secrecy Systems, where he says that the problem of good cipher design essentially one of finding difficult problems. We may construct our cipher in such a way that breaking the cipher is equivalent to solving laborious problems. So you want to construct a good cryptographic code, you need a very difficult mathematical problem. If you can construct your code in that way, based on a very difficult mathematical problem, then it will be difficult for the attacker to break your code, because the mathematical problem is difficult. So we would need difficult problems. Do we have them? Well, we didn't quite have them for a long time. Finally, in 1971, we got something. So what are laborious and difficult problems? Okay, there are two kinds of these problems. There are problems that we think they are difficult, and these problems are related to number theory normal. And there are problems that we can prove, so we can prove they are difficult, and mathematical terms are called NP-hard problems. And these are problems arising mainly from lattice theory, linear codes, or polynomial. So there are problems that we think are difficult, but we are not certain, and problems that we know they're difficult. Now, the funny thing is that when we started doing modern cryptography in 1976, most cryptographic systems, they are based on problems that we think difficult. We don't know if they are. And funny thing is that the quantum computer, if you can build a quantum computer, you will break all these problems. And so you will break all cryptographic systems which are based on discrete logarithm finite fields, discrete logarithm elliptic curves, integer factorization, and other number theory stuff. So don't ask me why, but when we started doing modern cryptography, we decided to use problems which were probably difficult, but not sure about that. So let's come back to blockchain. A blockchain is an infinite immutable blackboard. Okay, this is a picture, but how we can get this in practice? Well, we need a lot of stuff. Satoshi Nakamoto, 2008, in his revolutionary paper, Bitcoin, a peer-to-peer electronic cash system, he created the blockchain, which is this immutable stuff, and it needs two cryptographic algorithms. It needs a digital signature and hash functions. So there is a lot of stuff in the paper, not discussing Satoshi's paper now, but if you don't have digital signature and you don't have hash function, you can't do really a blockchain. So it's okay, beautiful paper. However, the digital signature which is used in Bitcoin is based on the supposed hardness of problems related to elliptic curves. We don't have any proof on the hardness of this problem. And unfortunately, a quantum computer could easily break the signature and steal all the millions of bitcoins in the world, billions, trillions of dollars. So this is a problem because we need some system that can resist the quantum computer well, but we don't know what will resist the quantum computer. We know what will resist a classical computer. Can't we start with that? In fact, there are cryptographic algorithms, including digital signature, which are based on problems whose hardness is proved, mathematical proof. And in my opinion, unsurprisingly, quantum computers do not have any significant advantage with respect to classical computers when it comes to provably hard problems. So a problem which is hard for a classical computer, you can prove it's hard apparently also for a quantum computer. So, okay, so if you want to build a cryptographic system based on provably hard problems, you are building what we call now post-quantum cryptography. Cryptography that might resist quantum computing. We don't know if it resists quantum computing, but it has a chance to. However, this introduces many practical issues. There are problems with the key size, the speed of computation. There are many problems. They're not so easy to apply. So here comes blockchain. We work on the Quadrans blockchain yellow paper. So the Quadrans Foundation is its own blockchain. It's a public blockchain. And I authored the yellow paper. And there we have selected and inserted some post-quantum signature inside that can be inserted in the Quadrans blockchain, and that could be implemented and integrated in a structure which is complex. Because the Quadrans blockchain that we design is rather complex, there's many things to do. So this could be done. Okay. Now, in particular, we worked on three families of post-quantum algorithms. We worked on signatures based on lattice theory. And why mathematicians like lattice theory? Well, there is an important result in complexity theory, which is recent, which says that if you have a random key, if you have a random instance of your problem, and you want to solve it, it's as hard to break as the worst case key. So when we work in cryptography, you don't take the hardest possible case. You construct a random key. That random key could be very easy to break. Who knows? The theory, complexity theory is usually based on worst case analysis, the worst case. But if the random key is easy to break, problem lattices have shown this advantage, that there are some proofs that apparently show that the random case is as hard as the worst possible case. And so this is very important. That's why the United States, they are selecting system based on lattices as the new standard. But we are not limited to lattices. We have worked on signatures based on linear codes. Okay, linear codes don't have this result between worst and average. They have another advantage. It's been proved that if you give a large part of the input, if you want a large part of the key, and I give you infinite preprocessing, I give you infinite time, infinite computers, even that, this will not help in solving the problem. Unless you have basically all the key. If you have only part of the key, you have infinite time, infinite energy, what you want. I give you infinite time. Still, this will not help in solving that. So this is also very interesting. That's the reason why we work also on this. And they are inserted in the Quadrans blockchain as well. And finally, we have also studied signature based on solving system of binary polynomial equations, which is called normally multivariate cryptography. Well, these systems, they are less popular, and one of the standards being proposed is called Rainbow, has been just broken recently. So they're not so popular, apparently they don't have any special properties like the other two families have. But we have a result. We have proved that the main decision problem associated to polynomial equation, which is called MQ, is actually this language is in fact isomorphic to the main decision problem used in linear codes, which is called MLD. So we have proved the isomorphism between the two languages, or if you prefer, between the two problems. So that's why we have added also signatures coming from this theory. Okay, that's it. Thank you.